Welcome to Dr. Nakamura's lecture series on structural dynamics, number C-2. Chapter 3, Free Vibration Response. 3.1, Solution of the equation of motion for SDOF. Let us solve the equation of motion for the SDOF system, equation 1, which does not include the damping and external force. This is a differential equation of ut, which can be solved by assuming u as a cosine omega t. A and omega are constant values. Putting the assumed u into equation 1, we get equation 2. A is not 0 because if A is 0, u is always 0. Cosine omega t is not always 0. So minus m omega square plus k must be 0. Therefore, omega is square root k over m, equation 3. T and f are obtained as equation 4 and 5. Let me explain what omega, t, f, and a mean. Look at the figure below. The displacement u has a cosine curve which varies with time t. A is the amplitude. Omega is angular frequency. T is the natural period which has the relation with omega. Omega times t equal 2 pi. F is the natural frequency which has the inverse of the period, and the unit is Hertz. Exercise 2.1. Find omega, f, and t with units of a single degree of freedom model with m equal 1.0 kilogram and k is 1.0 Newton per meter. Answer. Omega, natural circular frequency, is square root k over m, which is 1.0 radian per second. Use the SI unit. T and F are obtained by this formula. Natural period t is 6.28 seconds and the natural frequency is 0.159 Hertz. 3.2. Damped free vibration of a structure with SDOF. Equation 6 is the dynamic equation of SDOF model with a damper. The external force is 0. Suppose you pull it to the right at the initial time, then release it. It moves left and right. In other words, it vibrates without the external force. This is called free vibration. To solve this differential equation, we assume the displacement u as phi exponential st, which is a more general form than sine and cosine curve. Then we get equation 7. As phi and exponential est are not 0, the first term must be 0. This is a quadratic equation of S and gives S equal equation 8. In this equation, omega is equation 9 and H is the damping ratio defined by equation 10. Putting S to U in these equations, we can find U as equation 11 with omega d of equation 12. This is illustrated in the graph. A is the amplitude. The natural period t equals 2 pi over omega d, and phi is called phase. As you can see, the vibration gets smaller, which is due to the damping. There is another useful way to describe the effect of damping. Suppose at the time Tm, the displacement um is equation 13. One wave forward, at the time Tm plus 1, the displacement plus 1 becomes as equation 14. Then we define delta by logarithmic over plus 1 as shown in equation 15. H is much smaller than 1.0. Delta becomes 2 pi h. Delta is called logarithmic decrement, which is very useful to evaluate damping effect and widely used in practice. Exercise 2.2. Draw free vibration displacement ut for the cantilever beam, a single degree of freedom structure, with the following data. Mass m equal 1.0 kg, spring constant k equal 1.0 Newton per meter, and logarithmic decrement delta equal 0.005, 0.02, and 0.1. Displacement at t equals 0, u is 1.0 meter, and phase at t equals 0, phi is 0. Displacement u can be calculated by this equation. Omega is 1.0. H can be obtained by delta. This graph of displacement u for delta of 0.02 is drawn by Excel. This is for delta of 0.1. Clearly, the vibration diminishes faster for the larger damping ratio. Chapter 4. Response to harmonic loading. Harmonic loading means sine or cosine wave loading. Suppose a single degree of freedom model is subjected to an external load P0 cosine omega t. Its dynamic equation is described as equation 16. To solve this differential equation, let the both sides divide by m, equation 17. It is important to understand that omega 0 is the natural circular frequency of the structure and omega is the frequency of exciting force. The solution of equation 17 is assumed as equation 18. The structure is excited by the frequency of the external force omega. So, it is reasonable to think that the structure vibrates with this external load frequency. Putting equation 18 to equation 17, we get A and alpha as equation 19 and equation 20. MD is defined by A over P0 over K, which is the displacement when P0 acts statically. So, MD is the ratio of amplification against the static displacement. MD is higher with smaller damping ratio. Also, it has a sharp peak with omega over omega 0 equal 1. In other words, when the frequency of the external force agrees with the natural frequency of a structure. This phenomena is called as resonance, which should be avoided in designing structures. Exercise 2.3. Find MD for a SDOF structure with the following data. M equal 1.0 kilogram, K equal 1.0 Newton per meter, H equal 0.05, and P0 1.0 Newton, omega equal 0.5, 1.0, 2.0, and 3.0. Omega 0 is 1.0, and MD can be calculated by this equation. The results are shown in this table. When omega equals to omega 0 of 1.0, MD becomes the maximum value of 10.0. Here is the graph. When omega over omega 0 becomes large, MD decreases. That's all for this lecture. See you next lecture.